Lesson 5, the periodic table. So we're going to look at how the periodic table is arranged and some fun things it tells us. So when we talk about a vertical column in a periodic table, we call that a group. So we can see down here in this periodic table, we have group 1, so that's all of these elements. Group 2, group 3, etc., down the line. Group 18 is here. Group 18 is a fun one where I'm going to actually tell you, these all have different names, the groups, like the alkali metals, alkaline earth metals. We are not going to go into great depth about individual groups, but I am going to point out one very special group. We call this group the noble gases. We'll learn more about them in future lessons. When we talk about the row of the periodic table, we call that a period. And a period in math or in just language, it means something that repeats. And so we have some repeating qualities every period. And we'll learn more about that in future lessons as well. So this periodic table is fun. It looks like other ones we've seen before, in that we have the element name and atomic number, atomic mass, average atomic mass. But it also tells us about what state that each element is at room temperature and pressure. So we can look at the little key here. So things that are gas at room temperature have a little fun balloon. So hydrogen is a gas at room temperature, helium, neon, argon. Liquid, I think there's only one liquid at a room temperature. That's interesting. You can see if you can find it. Solids, many things, or most things, are solid at room temperature. You can see they all have this solid symbol. And then this is a fun one, synthetic. That means that these elements, and these are all down here, these really big elements with lots of protons and neutrons, they do not occur naturally in nature, but they have been synthesized in the lab before. They've gotten smaller elements to combine together to be big nuclei that make those synthetic elements. Now the other thing this table tells us is generally which elements are metals, metalloids, and nonmetals. So on your notes, you're going to make a few notes on your periodic table. What I'd like you to do is draw. Now your notes are in black and white, so you don't see the color, but I'd like you to draw a little kind of staircase here. All of these blue elements, these are all metals, so you can just write in metals like this. And then we're going to separate these out as well, draw this other staircase separating the green from the yellow. And these yellows are all non-metals. You can write that in. And then these ones in between have some properties of metals and some properties of non-metals. So we give them a fun name, metalloids. So in the video and questions embedded in the video, you're going to answer questions. You're going to try to find a few elements and state whether they are metals or nonmetals, and then what their states are in room temperature and pressure. And I know this periodic table is kind of hard to read. You might choose to combine it with your periodic table handout, which is easier to read, where you can see the full name and everything. Oops. Okay, coming back. Let's now look about general properties of metals versus nonmetals. So, what do all metals have in common? So let's imagine an actual familiar metal. Let's say we have the metal iron, like a big iron pan, those black cast iron pans you might cook with. And for our nonmetal, let's imagine a couple of different nonmetals. Wood is made of carbon and hydrogen. Those are both nonmetals. Water is made of hydrogen and oxygen, H2O. So water would be non-metal elements combined together. So let's think about the appearance of metals. So in general, metals are, wait for it, I gotta pull it up here. Metals are shiny. oops, shiny does not have any. They reflect light really well. And nonmetals are dull. Metals have a high melting point. It means you need a lot of heat to melt a metal. So you think about a chunk of iron, it's going to take a lot of heat to melt that. Whereas a nonmetal, like water is made of nonmetal elements, that is not going to take a lot of heat to melt ice, to go from ice to water. So those have low melting points. Ability to conduct electricity. Metals conduct electricity very well. That's why wires are made of metal, electrical wires. Nonmetals, like wood, if you try to run electricity through wood, it does not conduct electricity well. Now water, if it has, like ocean water has salt dissolved in it, which has ions, that actually does conduct electricity. Pool water conducts electricity well. But if it was just pure distilled water with no dissolved ions, it would not conduct electricity well. Ability to conduct heat. Metals conduct heat well too. If you put a metal on a stove or in a fire and you touch it, that will be hot. It will conduct the heat to your hand. Or you put it out in the sun, it will get hot quickly. Nonmetals are poor conductors of heat. Generally, metals are very dense. They have high density. Oops, density. Okay, wait. High density, and nonmetals have low density. So if you think about like oxygen gas, if you had a sample of oxygen gas, that would be really low density. You could have a big volume of it, like a big balloon of oxygen gas, and it would weigh very little. Whereas if you had the same volume as iron, it would be quite heavy. It'd be very dense. Oxygen gas would be not very dense at all. Malleability is a fun term. It's the ability to be shaped into sheets by pounding. So you could pound on iron and it would flatten out and you could shape it into a big sheet of iron, or other metals. You could do that. So metals are malleable, yes. Nonmetals not malleable, so they are brittle. So if you were to pound on ice, you could not flatten it into a sheet. It would shatter. Okay, the next part of our notes are atom fun facts. So we're going to look at this little slides I put together. For this, you're going to guess the answers for each one. And don't worry if you don't get them right. I won't be counting these for correctness, but I'd like you to kind of contemplate and think about them and enter your guess before the answer is revealed. So let's go to the slideshow that has these same questions here. And as we talk about the answers, you should record them here on your note sheet. Okay, so here's the atom fun facts. First question. If an atom was the size of a stadium, so think of a football stadium, how big would its nucleus be? So if we enlarged an atom all the way to the size of an enormous football stadium, and its nucleus was in the middle, and then its electrons were zooming around the nucleus in the size of a stadium, how big would that actual nucleus be inside of that stadium? Pause. It would only be the size of a blueberry. Crazy. We could put a tiny blueberry in an entire stadium. That would be the size of a nucleus if we enlarge the atom to the size of the whole stadium. So electrons contribute very little mass to the atom. They're just zooming around the outside and they take up a lot of space. It takes this many electrons to equal the size of just one proton. So most atoms are 99.9% empty space. So think of your body. It's made of atoms. All matter is made of atoms. Most of it's empty space. That's crazy. The nucleus is super tiny. There's little blueberries, and most of it's empty space. But because those electrons are zooming around so fast, they have the quality of it being, solid. Okay, next question. If we could magnify a hydrogen atom, so remember hydrogen atoms have one proton and one electron, right? If we could magnify it so that its nucleus were the size of a basketball, so we enlarge it, and the nucleus is a basketball, how far away would its electrons be whizzing around? How much space would they, sometimes they'd be close to the nucleus, but sometimes they'd be really far away. How far away could those electrons get and still be part of that hydrogen atom? 2 miles! So if you had a basketball and those electrons would be 2 miles away, like from our school to downtown Sebastopol. Crazy. All of the space between the electron and the basketball-sized nucleus is empty. What is the most abundant type of atom in the universe? So what element is most common in the universe? Of all those periodic table of elements, which one is the most common? Hydrogen! The most abundant type is hydrogen. Nearly 74% of the atoms in the entire Milky Way galaxy, that's the galaxy planet Earth is part of, nearly 74% of all those atoms are just hydrogen atoms. The smallest atom there is. What percentage of atoms do you replace in your body each year? So obviously we sweat, we breathe out, we eliminate, and things get recycled. The atoms get recycled in our body, and then we add new atoms by eating and drinking and breathing. So how many of those atoms are recycled, changed out each year? You have around 7 billion atoms in your body. 98% of them get replaced every year. Crazy. And here's a breakdown of the frequency of atoms in our body. 65% of the atoms in our body are oxygen, 18.5% are carbon, 9.5% are hydrogen, 3.3% are nitrogen, and then there's some more that are little trace elements. But we're changing those out all the time through our eating and breathing and urinating and all of breathing out, all of that. Okay, next fun fact. If we enlarged an orange to the size of Earth, what size would the atoms in that orange be? So we're going to have a huge, let's get the color orange here. Our orange is now the size of planet Earth. So all of its atoms have also gotten enlarged. So the atoms are much bigger than they were before. How big would they be now? They would only be the size of cherries. Atoms are so small that if we enlarge an orange all the way to the size of Earth, our entire Earth would be filled with cherries, and those would be the size of the atoms that make up the orange. Crazy. Okay, let's think of a copper penny. So that's just a penny, right? A penny. And does it contain more atoms in the copper penny or fewer than the number of people on Earth? So the number of people on Earth is greater than 8 billion at this point. I have to look up. So is there more or less than 8 billion atoms in a penny? There are way more. The number of atoms in a penny is 2.9 times 10 to the 22nd atoms. That means, scientific notation, 2.9, we have to move our decimal place 22 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we have to fill in all of those with zeros. Ooh, it's such a big number. So there's 5 trillion times more atoms in a penny than there are people on Earth. Their atoms are small, guys. So small. This has more fun facts if you want to go on that website and learn more fun facts about atoms. And that's it.